We started this week by talking about edges, then we went from edges to blobs to corners, and then talked about a few varieties of corner detectors, and talked about an important corner detector called SIFT, talked about a feature descriptor of how you would describe your corner as a vector, and then last lecture we also talked about image segmentation. Now we're also going to talk about other kinds of feature spaces that people worked on in computer vision before deep learning came into the picture. That's going to be the focus of this lecture. One of the other important feature representations that was developed was known as shape context. Shape context was about taking a pixel and placing and getting a log polar representation of the neighborhood around the pixel using this kind of a representation. So you define a coordinate system in 2 dimensions that's parameterized by logarithmic distance from the origin, which is the pixel at which you're trying to get the representation, as well as the angle. So for each point that you consider, you would count the number of points in each log polar bin around that particular pixel. So if this log polar representation, you can see that there are perhaps something like 1, 2, 3 and 4 regions in terms of angular distance, in terms of log distance, and then 12 bins in terms of the angles themselves. So as you can see, there's more precision for nearby points, very similar to the Gaussian kernel, where you give more weightage to nearby points, and then more flexibility for farther points around that pixel where we are considering the representation. To some extent, this method, this representation, is translation and scale invariant, depending on the size of the neighborhood you take. Let's study this in a bit more detail. So let's consider 2 different images. So now if you consider this pixel, so there are, if you cannot see carefully, this is a circle, this is a triangle, and this is a rhombus. So if you can see here, you can and the first one is the representation of the circle, the second one is the representation of the rhombus, and the third one is the representation of the triangle. How did these representations come? There are 5 bins in terms of log r, or the log radial distance, and 12 bins in terms of your theta, or your angles around the center. So you can see here that the circle and the rhombus have very similar representations. So one could consider these 2 points as correspondence points between these 2 representations, or these 2 images of A. And when do we say 2 points are in correspondence? We say 2 points are in correspondence if they minimize a value of Cij, where Cij, I and j being 2 pixels that you're trying to measure, and Cij is defined as summation over k hik minus hjk whole square by hik plus hjk. And hik and hjk are the histogram locations in the around the ith pixel and in the representation around the jth pixel. Hi is the histogram of the number of pixels in each of those bins around the ith pixel, and hi similarly for the jth pixel. Hi of k would correspond to the count in one of those bins. And what is small k or capital K? Capital K is the total number of bins, right? So for hi of k would be the count in one of those bins. So when would Cij get minimized? When the numerator is 0, or the histograms exactly match, or when the histograms are fairly close to each other, you would ensure that these values will turn out to be low. The denominator ensures that you're also considering the number of pixels considered while evaluating this. Very similar to how we spoke about in normalized cut and min cut. The denominator helps in normalizing based on the number of pixels that you're considering for your studies. So once you get these correspondence points between two images based on the representation, you could then do a one-to-one matching sequentially between these points, between these correspondence points. And when a distance is less than a threshold, this kind of an approach was used to check for a shape match, not just a point match, but matching shapes between two different images. That's the reason it was called a shape context. Another feature space or important method that was proposed is known as the MSER, or the maximally stable extremal regions. This was a method for blob detection based on watershed segmentation. So we just saw image segmentation in the previous lecture. Using one of those methods, which is simple watershed segmentation, that method is used to come up with a method for MSER, or maximally stable extremal regions. And how does this work? You identify regions in an image that stay nearly the same as you keep varying a threshold. Let's try to describe this. So you would ideally sweep the threshold of an intensity going from white to black or black to white, and in each step you're simply thresholding based on that particular intensity value. So if you have an intensity of 75, everything above that is white and everything below that is black, a simple thresholding operation. Then you extract connected components within that thresholded image, and the final region descriptors serve as the features. Let's see this more clearly with some illustrations. So let's say we start thresholding the images about a particular intensity level G, so which means you considered a threshold G, and everything above that is considered to be white and everything below that is considered to be black. So you binary threshold your image based on the threshold G. Clearly, when you threshold, you're going to see a bunch of blobs or collections of pixels appear. They're going to be cohesive regions that appear together when you threshold. So, and as you increase the value or decrease the value of G, whatever it be, in this case, if you say decrease the value of G, newer regions would start appearing. If you decrease the value of G, you're now giving a lower threshold for considering regions to be white and the rest of them to be black. So there will be more regions that start appearing with white pixel values in the thresholded image. And if you increase G, things would start coalescing, and these regions that get developed as you keep changing G values can be depicted in a tree-like structure. It's very similar to region merging and region splitting. As you reduce G, some regions may merge. As you increase G, regions may split based on their intensity values. So now what do you do with this? So let regions at a particular G level be denoted as R1G to R2, R2, RNG. Let's say there are small n regions, each corresponding to one particular threshold G, where the cardinality of Rij denotes the total number of pixels in one of those regions Rij. Then we define a quantity psi, which is given by cardinality of Rj G minus delta minus cardinality of Rk, another region, G plus delta by Ri. Rj and Rk are parents and children of Ri, of that corresponding region, at slightly different thresholds G minus delta and G plus delta. Let's try to study this a bit more carefully. Remember again that Rij is one of the regions that you're considering at the threshold value G. Now, if you subtract a little value, G minus delta, then you would get a parent region which is perhaps larger than Ri. Remember, when you subtract the threshold, the white region would probably get bigger. So you're going to have a parent region Rk, which is defined at G minus delta. And at G plus delta, when you increase the threshold, the region may get smaller. The white region may get smaller. We're going to define that as a child, and that's defined by Rk. And if this quantity psi, which is the difference between Rj and Rk, is below a user defined threshold, you would call those regions to be maximally stable extremal regions. Remember, if it is smaller than a threshold, it simply means that there is almost no change between the parent and the child. If there is a lot of change, then you probably need to expand a little bit further before calling it a stable or an extremal region. Here is a visual illustration. So this is the input image. As you can see, it has some characters in it. And when you set your threshold to be 75, assuming again that you use 8 bits to represent a pixel, so values between 0 and 255, you see the regions not very clearly defined. But when you go to G is equal to 105, you see regions getting slightly more well defined. And you can see that at 135, there are a few changes, but not much. At 165, very minor changes, not much again. At 195, almost no change. At 225, things again start going to black because the threshold is very high. So you could now represent that as a tree where you start with a region. That region becomes 2 regions at level G is equal to 105, and region 2 becomes region 4 and region 8 at level G is equal to 135, and so on and so forth to build the rest of the tree. So finally, as you can see, at level G is equal to 195, you have 2 regions, one with the K and the other with an R, which is what you were originally looking for. So this gives you one way of separating different regions. So this is not exactly a corner detector, but another method to separate regions. So another way, we said that it could also be used as a blob detector, and here is an example for doing blob detection using maximally stable extremal regions. So given this input image, if you go from white to black or black to white, the top 2 rows depict when you go from white to black, and the bottom 2 rows depict when you go from black to white. If you go from white to black, you start with a high threshold, and then you decrease the threshold, more regions in black start showing up. You decrease the threshold, more regions in black start showing up, and the regions start merging, and you're finally left with, even as you change the threshold, when regions don't change, you know that that's actually a stable blob representation of your original image. Remember, when you see it from a black to white, you're going to look at it in terms of merging. So you're going to say that when it's black, obviously there's no region. When you slightly increase, certain regions start showing up. And as you keep increasing the threshold this way and then go up to the 3rd row, you can see more stable regions showing as you go forward. So this is another approach to find out blobs or regions in an image, called maximally stable extremal regions. Another famous method, you probably have already been exposed to this when we talked about SIFT, but this method was also independently developed to be able to detect humans in images, is known as histograms of oriented gradients, or popularly known as HOG or HOG. So this originally was proposed in a paper that was used for human detection in different kinds of images. So let's say you had a portion of an image or an image containing a human. So at each location where the window is applied, you compute gradients. Remember, computing gradients is simply an edge detector, whatever edge detector you want to choose. And then you divide the entire gradient image into a uniformly spaced grid. And then for every 2 cross 2 block in this grid, you compute your orientations of the gradients. Very similar to how we talked about it for SIFT. You would have, say, multiple orientations. Let's say you define 8 different orientations. You see how many pixels in that block had orientations of gradients in certain bins. And you bin them to get a histogram for each 2 cross 2 block. and you do this over overlapping 2 cross 2 blocks, which gives you the histograms that you see on this image on every grid center. So you can see here that each of these is just a different way of drawing a histogram. Remember again, if you recall, something like this was just another way of drawing a histogram with 8 bins in 8 directions, where the length of the arrow denotes the frequency count in each of those bins. Right? This is just another way of representing that, or this could be another way of representing the gradient orientations and getting the histogram. So the histogram of oriented gradients was shown to be very effective for detecting humans in an image in the mid-2000s. And this was also improved upon to give what is known as pyramidal hog or p-hog, where at every step you divided the image into parts and constructed a HOG representation for each part individually and then concatenated all of them to form a representation. How do you do this? You divide an image into 2L cross 2L cells at each pyramid level L. So if L was 1, you would divide it into the entire image into a 2 cross 2 cells, 4 cells. Or if L was 2, you would divide it into 4 cross 4, so on and so forth. Now for each of these cells, you extract HOG descriptors, just the way we spoke about on the previous slide, and then you concatenate the HOGs at different pyramid levels to give an entire histogram of oriented gradients representation. So as you can see, this can be done in several ways. You would get a histogram of oriented gradients for each cell and concatenate all of them, and then you would get a histogram of oriented gradient at L is equal to 0, L is equal to 1, and you can concatenate all of this also to get your final representation. So this method was shown to capture spatial relationships between, say, objects a little bit better than HOG, which doesn't do this at a pyramid level. Another popular method, which was extensively used for face images in particular, human faces, was known as local binary patterns. Local binary patterns had an interesting idea where, given an image, for every pixel you take, for example, a 3 cross 3 neighborhood around a pixel. So this is the IIT Hyderabad logo. So you consider a pixel and a 3 cross 3 neighborhood around the pixel, write down the intensity values of those pixels. Now with respect to the central pixel, you decide if each of the other pixels around it were lower or higher. If it was lower, you would set a 0. If it is equal or higher, you can set it to 1. That now gives you a binary pattern around the central pixel. Once you define a canonical representation, which means you say I'll start at the top left and then go in a circular manner, you can define a binary representation for this particular pixel. So once again, I'll repeat that. So you define a binary representation based on how each pixel is related to the central pixel's intensity. So now this value is now 15 in decimal, and you replace that pixel's value with 15. Other values around it would similarly be obtained by doing an LBP position at that particular pixel, and so on and so forth. Now what do you do with this new LBP representation? Before we go there, you can also define neighborhoods in multiple ways. We said you would take a 3 by 3 neighborhood and take the 8 pixels around it. That may not be always the case. You can vary 2 different parameters here. You can define your radius R. You can also define the number of neighbors P. So you can have a particular radius where you want to compute your local binary pattern width. That need not be the immediate neighbor. It can be a radius of 4-5 pixels around the central pixel. And you can also define how many neighbors you want at that radius. So you could define P is equal to 8, the number of neighbors is 8, and R is equal to 2. As you can see, that's the example that you see on this particular image. Similarly, you could have a closer neighborhood, R is equal to 1, but the number of neighbors to be the same, P is equal to 8. Similarly, you could have at r is equal to 2, you could increase the number of neighbors and make it p is equal to 12, and at r is equal to 3, further out, you could still have 12 neighbors. Once you define the neighbors, if these neighbors lie in between 2 pixels, you can use bilinear interpolation to get those values. So once you define r and p, based on those values, you would get a binary pattern around the central pixel. You write that out in a circular manner as a binary number, convert it into decimal, and replace the central pixel with that particular value. What do you do with that? So once you get an LBP result, which is your LBP intensity for each pixel, remember the previous process that we talked about in the earlier slide, gives you one decimal for each pixel around which you considered the neighborhood. So you could now construct such an image for every pixel. You could repeat the same thing and construct such an LBP image. Once you do this, you divide the LBP result into regions or grids, and once again you can get a histogram of each region, the number of pixels in each region in this particular case, and concatenate all of them to be able to get a single representation for a region or an entire image. In this case, we're not considering the gradients, it's simply the histogram, but you could also improve LBP to consider gradients in each cell, so on and so forth. There have been several improvements of LBP or local binary patterns that have considered these kinds of variations. So here is a quick summary of various feature detectors. We have seen some of them. We may not have the scope to see all of them, but you're welcome to look at the source of this particular table to understand more features. But you can view all features in terms of whether they are corner detectors, blob detectors, or do they help in finding regions, whether they are rotation invariant, scale invariant, affine invariant, how repeatable are they? Remember, repeatability is about ensuring that if you found a particular pixel to be a corner in a particular image, if you had the same image taken from a different angle in another picture, or same scene taken as a picture in another angle, that corner should also be detected as a corner in the second image. This is known as repeatability. How good is the localization accuracy? Remember, we talked about localization accuracy even for the canny edge detector, where we said, is the point exactly where it should be, or is it a few pixels away from the actual corner that we know? How robust is the method to noise, and how fast is the method? So these are various parameters in which, using which you can evaluate the goodness of the methods that we have discussed so far. So the Harris corner detector, let's take a few of them and just go over them. The Harris is a corner detector. It is rotation invariant, as we have seen, not necessarily scale or affine invariant, as we already saw. It's fairly repeatable. It's reasonably good with localization accuracy, robustness, as well as efficiency. Let's take another one. Let's consider SURF, which is an improvement over SIFT that we saw a couple of lectures back, which is a corner detector or a blob detector. It can be used either way. It is rotation invariant and scale invariant. That's the purpose of SIFT and SURF, to be scale invariant. It's in the name of SIFT itself. And it's also fairly repeatable, fairly accurate in terms of localization, robustness, and is extremely efficient. We saw that SURF is almost 3 times as fast as SIFT. So you can similarly look at, say, MSER, which is the one that we just saw a few slides ago, is a region detector, which is reasonably rotation invariant, scale invariant, and affine invariant. And it's also is repeatable, accurate in terms of localization, robustness, and efficiency. For more details of other feature detectors, please look at this in the references, and you can look at the paper to get a more detailed survey of other feature extractors. Why are we not discussing each of these is what we're going to talk about next, which is a lot of representations of images that used to be used in the pre-deep learning era are no longer relevant because of the success of deep learning in extracting features that are extremely good for various computer vision tasks. Remember when we talked about the history of deep learning, we said that in the mid-1960s, Marvin Minsky started out with a summer project to be able to solve the problem of computer vision, but many decades later, deep learning has been able to significantly make that progress at this time. So the homework for this is going to be reading chapters 4.1.1 and 4.1.2. If you're further interested about other feature detectors, please do read some of these links as well as some of these references. In particular, this reference gives an overview of various different feature detectors if you're interested.